Ah, pardon, c'est juste que... Ok, now it's good. Merci, désolé. Est-ce qu'on est tout bon côté technique? Ouais, super. Michael, prêt? Eh ben, bonjour à toutes et à tous. Bienvenue pour la soutenance de thèse de monsieur Michael Salihoglu, qui va nous parler dans quelques instants de la HP Adaptation for K-Exact Finite Volume Schemes. Avant de vous laisser la parole, je présente brièvement les membres du jury qui vont évaluer ce travail. Nous avons monsieur Carl Olivier Gouche, qui est professeur à the University of British Columbia, qui est en visioconférence. Nous avons monsieur Mario Ricciotto, qui est directeur de recherche à l'INRIA Bordeaux, qui est aussi à distance. Dans la salle, nous avons monsieur Frédéric Allosé, qui est de l'INRIA. Nous avons également monsieur Grégoire Pont, qui est ingénieur de recherche à Airbus. Et nous avons les deux directrices de thèse, madame Anka Belmé et madame Paola Cinella. Et, pardon, je suis moi-même Régis Marchiano, professeur ici à Sorbonne Université. Donc, nous vous laissons 45 minutes pour vous présenter les travaux. Et puis ensuite, il y aura une traditionnelle séance de questions et de commentaires. In English, and I think that your presentation is also in English, so you have the floor now.
Thank you, Mr. President, and thank you everybody for coming to my presentation. So today I'm going to talk about what I did during my 3 years of PhD about HP adaptation for K-exact finite volume schemes under the supervision of Paola Cinella and Anka Belmé. So this PhD is part of the MAMBO project. So MAMBO stands for méthode avancée pour la modélisation du bruit moteur et avion. And it is funded by the DGAC, so the General Direction of Civil Aviation. So this project is composed by numerous aerodynamic companies such as Afin, Ariane Group and Airbus. And this PhD in particular was in collaboration with Ariane Group and Airbus. And more specifically, the solver that we used is the one that is developed by Ariane Group. So the goal of this project is to improve the representation of aerodynamic noise sources in turbulent flows. So for example, here on the right, we have an example of these aeroacoustic noise sources in the wake of a turbulent jet. So when we solve partial differential equations in order to obtain a solution for physical flow, we come across very complex phenomena such as shock wave, turbulence, boundary layer, etc. So here we have an example of this with showcasing a supersonic flow around a cylinder at Mach 3. So here, as the flow encounters the cylinder, we have a bow shock that forms before the cylinder, which creates a sharp increase in density and temperature. Then the wake is which induces the creation of these vortices. The interaction between the shocks and the low pressure region induces the creation of even more vortices, and all these structure merge and interact with each other, creating an even more complex flow pattern. So now the question is, how do we resolve efficiently such problem? So in order to answer this question, we have two main solutions. So first, we use high order methods, and we can also increase the mesh resolution. However, the problem with these two solutions is that they often come with high computational cost, and the remeshing part can be at times tedious, and in some geometries can be highly complex. So one solution for this is the use of adaptive methods. So in this presentation, first I will be talking about a small state-of-the-art on adaptive methods. In a second part, I will talk about the governing equations and all the numerical methods that we have used in this PhD. Then in a third part, I will talk about the two adaptation strategy that we have developed, so P adaptation and HP adaptation. After that, I will talk about the results we obtained with both of these adaptation methods. And finally, I will conclude on these results and give some perspectives for future studies. So So first, adaptive method. So in CFD simulations, the numerical errors can arise from various sources. So, for example, discretization errors, time integration errors, model errors, etc., interpolation, or they can also come from boundary conditions. And in this PhD in particular, we will focus our attention on two of them, which are H, which are the mesh cell size, and P, which is the order of the numerical scheme. So here we have the impact of both of these parameters on a CFD solution. So on the left, the impact of the mesh on the solution, so H, and the impact of the order of accuracy, P. So first, if we look at the example of the at the bottom, we have the solutions that are obtained with the meshes on top. So we can see that by using a coarse mesh, we obtain a smeared and inaccurate result. However, using the finer mesh, it gives us a more localized, more accurate results. However, using the finer mesh also comes with a higher computational cost. Next, if we look at the impact of the order of accuracy, we can see that if we choose to computational cost. We also faced several challenges using high order methods because when we use a high order polynomial to interpolate a solution with a steep change, we come across spurious oscillations that decrease the solution's accuracy. So here, one way to solve this problem is to use low order methods in these regions. And then when we have insufficient resolution when trying to evaluate a derivative on a steep change of the solution, so this insufficient resolution will give us a poor slope approximation. So one way to solve this problem is to increase the resolution in these regions of the flow. So in order to circumvent these two problems, in this PhD, we will focus our attention on two adaptation methods. The first one is H adaptation, which is the adaptation of the mesh cell size, and P adaptation, which is the adaptation of the order of accuracy. So on the left, we have an example of mesh adaptation. So here we can see that, so on the right, we have the pressure isolines that are obtained with the meshes on the left. So we can see that by using a coarse mesh, we obtain smeared isolines. Next, by using a much finer mesh, we obtain sharper isolines. And by selectively refining a small fraction of the cells, we obtain sharper isolines by only refining a small fraction of these cells. Next, on the right, we have an example of P adaptation. So we have an order distribution for a flow around a cylinder at Reynolds 40. So at this Reynolds, the recirculation bubble behind the cylinder is attached to the cylinder. And in this case, we can see that the P adaptation algorithm mainly increased the order in important areas of the flow. So for example, here it is around the cylinder. We can see that far from the obstacle, the order is decreased. Next, we have the combination of these two adaptation methods, which is HP adaptation. So it is generally used in the context of discontinuous Galerkin methods, because it is more fitted for these kinds of methods, because in DG methods, the order usually depends on the internal degrees of freedom. But the problem with this method is that when the shock is not exactly at the interface between the cells, we obtain spurious oscillations that decreases the accuracy of the solution. So one way to circumvent that problem is to use HP adaptation to lower the order and refine the mesh in the discontinuities. And when the flow is smooth, we obtain an exponential convergence rate. Now, HP adaptation is very scarcely studied for finite volume methods because it is much less fitted for these types of methods because the order now depends usually on the first, second, or even third neighbors. So here we have, to my knowledge, the only example of HP adaptation that was used with HP adaptation. So here we can see we have the mesh and order distribution obtained for a transonic flow around a NACA 12 airfoil. So this was a paper from Jalali and collaborators. And we can see that they decreased on the strong shock on the upper surface. They decreased the order of accuracy and also refined the mesh. And in other areas of the flow, for example, on the leading edge and the weak shock, they increased the order of accuracy while also refining the mesh. Now, we also know that finite volume methods are known for being very robust, especially for shock capturing using limiters. So the way we are going to implement HP adaptation in our case, so contrary to the one that was done by Jalali and collaborators, is to optimize the computational time and the accuracy of the solution. So then comes another question. So where do we refine the mesh, and where we increase or decrease the order of accuracy? So in other terms, what refinement criteria do we use? So if we look at what is done in the literature, we can first look at the error estimator that was developed by Basile and collaborators, which is the small scale energy density, so SSED estimator, which gives an estimation of the error made by the highest mode of the solution. So here it is simply the difference in momentum between an approximation at order p and an approximation made at an order p minus 1. So this was used in the context of discontinuous Galerkin method and for turbulent flows. Next, we can also use Hessian-based criteria. So here it is a criterion that is mainly used in the mesh adaptation community. So here I've cited two examples, so Walkers and collaborators and Alose and collaborators. So why do they use these Hessian-based criteria? First, because it is an error bound for the second order scheme, and then because it gives a good indication of the error direction. So it is very useful when using anisotropic mesh adaptation, so whether it be anisotropic AMR or anisotropic metric-based mesh adaptation. And then finally, we also have adjoint-based criteria, which are very efficient when you want a good approximation of the solution of a specific functional. Now here we have an example of an adjoint-based criteria, which was studied by Jalali and collaborators. So here they calculate their error estimator using the discrete adjoint solution and the high-order discrete operator used on a low-order solution. However, the problem with adjoint-based criteria is that they require the solution to the adjoint problem, which is not often the case for CFD solvers, and especially in industrial CFD solvers. So we can see that we have no universal choice for adaptation criteria. So now the challenges we faced in this PhD are the following. So the first one is which criterion do we use for adaptation? Next, how do we develop a p-adaptation technique for finite volume methods? And then the final challenge is how do we combine this p-adaptation that we have developed with mesh adaptation? So to answer all of these questions, first I'm going to talk about the numerical methods, and then after that I'm going to talk about the two adaptation methods that we have implemented. But first, a quick word on the flow solver that we used. So it is called FluSepa. It is a 3D self-centered compressible unsteady viscous reactive finite volume flow code that is developed by Ariane Group. So it uses a conservative grid technique with intersections. For mesh refinement, it uses 3D adaptive mesh refinement, so AMR, on hexahedral elements. So this means that every hexahedral will be divided into 8 smaller hexahedral isotropically. Then for temporal discretization, it uses, for the explicit temporal discretization, it uses Freund's method with adaptive time step. And then for the implicit temporal discretization, it uses the backward Euler method. And then finally, for the numerical discretization, it uses the successive correction k-exact finite volume scheme, which I am going to describe now. So in this solver, we solve the Navier-Stokes in finite volume formulation, which is given here, in which W are the mean density, are the mean conservative variables. So for example, the mean density, mean momentum, etc. And F is the flux that is calculated at the interface between two cells. So here, AGK. So if we take the example here with the cell in red and the cell in blue, so the red being omega j and the blue one being omega k. AGK is simply the interface between the two, and gamma is the point at which we will reconstruct the cell center pointwise value. So in our case, k-exact scheme stands for the fact that we approximate our solution with a polynomial of degree k. So for the one exact scheme, we will linearly interpolate the cell center pointwise value here at gamma with a polynomial of degree 1. And for the two exact scheme with a polynomial of degree 2. So this numerical scheme can be divided into 5 main steps. So the first one is when we go from mean conservative values to primitive values. So we go from mean density, mean momentum to pressure, temperature, and the velocity component. Then in a second step, we go from primitive to volume average through a correction step for the two exact scheme, which is highlighted here in red. So this correction step is, so I've given here an example for velocity. So to compute this correction, we need the mean density, the second order volume moment, and the gradient of the density and the gradient of velocity. Then in a third step, we go from volume average to cell center pointwise value, again through a correction step that uses the second derivatives. Then in a fourth step, we go from cell center pointwise value to the face at gamma. So for the one exact scheme, we use a polynomial of order 1, so we use the gradient and the cell center pointwise value, and the gradient has to be calculated with an accuracy of order 1. And for the two exact scheme, we need the cell center pointwise value, the gradient that is now calculated with an order of accuracy 2, and the second derivative here that is calculated with an accuracy of order 1. And then the final step is the computation of the fluxes and the integration with, again, a correction step for the two exact scheme. So a very important part of this numerical scheme is the fourth part, in which we reconstruct the values at gamma. So the derivatives in our case are approximated with a Casey-Green method, and in order to ensure consistency on irregular grids, these derivatives are corrected using correction matrices, which account for the local mesh deformation. So this is how, for the one exact scheme, we are able to obtain a gradient with an accuracy of order 1, even on irregular grids. And for the two exact scheme, the gradient with an order of accuracy 2, and a second derivative with an order of accuracy 1. So now that we have talked about the numerical methods that we used, I'm going to present the two adaptation strategies, so P adaptation and HP adaptation. But first, I'm going to talk about the error estimator that we have developed. So the error estimator it takes the advantage of the iterative nature of our numerical scheme. Since we have previously seen that at step 2, when we go from primitive to volume average, we add a correction for the two exact scheme. And when we go from volume average to cell center pointwise, we also add another correction that uses the second derivative. So at first, in this study, we defined an error estimator, here delta, which was simply the difference between the cell center pointwise value at order 3 and the cell center pointwise value at order 2. So we were simply adding both of the corrections from step 1 and 2. So it was first designed for p-adaptation in order to show us the zones where where the order of accuracy needs to be increased. But the zones where the order must be increased in our case are also the zones where calculating the second derivatives are necessary. So we change our error estimator and we defined a low order proxy of this error estimator. So it is simply the difference between the average primitive values at order 3 and 2. So our error estimator is simply the correction step at the second step of the whole numerical scheme. So we remove the second term that requires the calculation of the second derivatives. So here I have given a reminder for velocity. So we use the mean density, the second order volume moment, and the gradient of density and velocity. But these gradients are calculated with an accuracy of order 1 in our case, since they are not corrected by the second derivative. And then finally, our error estimator is here epsilon, which is simply the normalized value of delta. So epsilon is between 0 and 1. So now I'm going to talk about the p-adaptation method that we have implemented. So the usual method we found in the literature is to use low order in singularities, to use high order in high error smooth regions of the flow, but that requires the calculation of a smoothness criterion. And then we use second order elsewhere. So now the question is, how do we develop a p-adaptation strategy for the previous scheme that we have just presented, so the successive correction k-exact finite volume scheme? So here's the algorithm. So first we compute an error estimator, epsilon, in each cell, and then we define a critical threshold, NC here. And if our error estimator is above this critical threshold here, the cell is marked for the 2 exact scheme. And if it is not, the cell is marked for the 1 exact scheme. And for all the cells marked for the 1 exact scheme, we skip all the correction steps, and we don't calculate any additional terms. So for example, at step 2 and 3, we saw that we added correction. For these cells, we don't add the corrections, both of these corrections, and we also don't calculate any of the second derivative. So this is how we save some computational time. So to summarize our p-adaptation strategy, we use high order, so in our case, third order, in high error regions, even in singularities with the limiter active. So, and we use second order elsewhere. So this greatly differs from the usual p-adaptation we found in the literature. Because in our case, we want to keep the third order even in the, for example, here on the strong shock, because we want to keep information about the gradient and the second derivative to prevent the solution from being calculated with the 0 exact scheme. We also need to enforce a conservation property. So here we have an example of a 1 exact cell that is followed by two exact cells. So at the interface between the 1 exact and the 2 exact cell, at the left of this interface, the value can be reconstructed with the gradient, and at the right with the gradient and the second derivative. So we need to enforce the same reconstruction on both sides of the interface, and the flux has to be calculated with the second order formulae. So we have also tried to do implemented a p-adaptation method that included the 0 exact scheme, but it led to suboptimal results and also a drastic drop in accuracy if the smoothness criterion was not set correctly. So p-adaptation also has its limitation, because when we have a highly unsteady and feature-rich test case on a coarse grid, increasing the accuracy up to third order sometimes does not suffice. So on top of p-adaptation, we add mesh adaptation to further enhance the accuracy and the mesh resolution. So now the question is, how do we combine the p-adaptation method that we have developed with H-adaptation? So here we simply updated our p-adaptation algorithm to merge it with h-adaptation. So now we still compute the same error estimator, and we define two critical thresholds. So first NC here, which is the same critical threshold as p-adaptation, and we define another threshold, which is the upper threshold. So in this case, if the error estimator is above both of these critical thresholds, the cell is marked for the 2 exact scheme and for refinement. If it is below the first threshold but still above the upper threshold, it is only marked for the 1 exact scheme and not refined. So now that we have talked about the 2 adaptation algorithms that we have implemented, we need to assess their performances on a set of numerical test cases. So first, in this part, I'm going to talk about the results we obtained with the p-adaptation algorithm. So in this presentation, I won't be talking about all the NACA 12 configuration, but instead, I'll be talking about the results on the unsteady laminar transonic flow over a 2D cylinder at Reynolds 300, and on the inviscid transonic flow over an Onera M6 wing. So first, the results on the unsteady laminar transonic flow. So it is at a Mach number of 0.8 and a Reynolds number of 300. So in this case, we have a recirculation bubble that forms behind the cylinder. It becomes unstable and creates vortices in the wake of the cylinder. And we also have a lambda shock pattern that appears on both sides of the cylinder. The mesh we use in this case is the one that is on the right here, where we have regular quadrangle around the cylinder, and the rest of the domain is meshed with triangular elements. So here on the left, we have the reconstruction error criterion for this flow. And on the right, we have the order distribution also for this flow, which is given by the, if we set a critical threshold of 1% of the maximum error. So in this case, we managed to mark most of the front of the cylinder, the shock here and the lambda shock pattern, and also the vortices in the wake of the cylinder for the 2 exact scheme. And the rest of the domain is marked for the 1 exact scheme in our case. So now if we plot the lift coefficient around the cylinder, and we calculate the fast Fourier transform on 15 periods of the signal, and we compute it for the 1 exact, the 2 exact, and with p-adaptation, and we compare ourselves to the Stroll number that has been obtained in the literature. So for example, here by these on these 3 papers. So we can see that they obtain a Stroll number of 0.165. So first, if we compare the results from the 1 exact and the obtained with the 1 exact and the 2 exact scheme, we can see that the results obtained with the 2 exact scheme are closer to the reference values. And now if we look at the results from p-adaptation, we can see that we obtain a Stroll number that is closer to the results obtained with the 2 exact scheme rather than the 1 exact scheme. Now, if we look at the CPU time, we can see that in our case, by marking only 30% of the cells for the 2 exact scheme, we managed to save 20% of the CPU time. Next, if we move to a 3D inviscid case about the inviscid transonic flow over an Onera M6 wing, so at a transonic Mach number and this angle of attack. So in this configuration, we have a lambda shock pattern that appears on the upper surface of the airfoil. And the mesh used in this case is the one that we have here on the right, where we have regular hexahedral on the wing body and around the wing body, and then the rest of the domain is meshed with a mix of tetrahedron and hexahedron. So here on the left we have the reconstruction error criterion, and on the right we have the order distribution if we set a critical threshold of 1% of the maximum error. So in this case, by choosing this threshold, we manage to mark most of the airfoil for the two exact scheme, and also the lambda shock pattern on the upper surface. And the rest of the domain is marked for the one exact scheme. Now, in this case, to assess the performance of the P-adaptation algorithm, we looked at a specific section of the wing of the airfoil. So for example, here, this section, and we extracted at the left the Mach number distribution, and at the right, the entropy deviation. So why do we look at both of these values? So first, the Mach number, because it gives us a good indication of the correct computation of the flow. And why do we look at entropy deviation? It is because for an inviscid flow, the entropy is supposed to remain constant. So if it deviates from this constant behavior, then we are directly looking at numerical errors. So first, if we look at the Mach number distribution, see here we have the Mach number distribution on the upper surface and the lower surface. And we can see that on the upper surface, we have two jumps in Mach number. So this is because we are looking at both of the branches of the lambda shock. And we can see here that we have a good agreement between the results obtained with P-adaptation and the results obtained with the two exact scheme. Now, if we look at entropy deviation, we see the both of the jumps, with one being stronger than the other one. It is because we are looking here, we are looking at the strong branch of the lambda shock. And again, just like the Mach number distribution, we have a good agreement between the result from P-adaptation and the two exact scheme. Now, if we look at the CPU time and the number of cells marked for the two exact scheme, we can see that in this case, by marking only 20% of the cells for the two exact scheme, we managed to save 60% of the CPU time. So now I'm going to talk about the results I obtained with HP adaptation. So first, I'll be talking about the results obtained with the shockwave impingement on a mixing layer at Reynolds 500. And then finally, I will talk about the 2D viscous shock tube at Reynolds 1000. So this first test case of the shockwave impingement on a mixing layer was first studied by Yi and collaborators. So in this test case, at the left of the domain, we have a hyperbolic tangent velocity profile that creates this unstable mixing layer. This unstable mixing layer will interact with a oblique shock that originates from the top left of the domain. This oblique shock will then be deflected. It will then be reflected at the lower wall of the computational domain and interact again with the unstable mixing layer here. So first, what we try to do is to compute this test case on a coarse mesh of 200 times 80 elements with the two exact scheme. And we can see that most of the details of the test case are missing. So the oblique shock is completely dissipated and calculated with a bad angle here. The mixing layer doesn't become unstable, and if it becomes unstable, the vortices are immediately dissipated. So we can see that most of the physics of the phenomenon are missing from the calculation. So on top of this coarse mesh, we add the HP adaptation algorithm that we have implemented. So here at the top, we have the order distribution, and at the bottom, we have the adapted mesh with two levels of refinement. And in this case, we can see that by using a critical threshold at 1% of the maximum error, we managed to mark the oblique shock and the deflected oblique shock, and also most of the unstable mixing layer for the two exact scheme and also for refinement. And the rest of the domain is marked for the one exact scheme. So now if we look at the results obtained with HP adaptation results at the bottom, and we compare ourselves to the results obtained by Yi and collaborators on a 640 times 160 grid with a 6-order finite difference scheme, we can see that now most of the details of the test case are now present. So the unstable does in fact become unstable. The oblique shock is much more sharply resolved. And we have the two interaction with the unstable mixing layer and the oblique shock. And we can also see that we correctly computed the reflection point here at the lower wall. So to further assess the performance of our HP adaptation, we extract the pressure across the shear layers here. So here we can see both of the interaction between the unstable mixing layer and the oblique shock. And here we plotted the results obtained with, in blue, H adaptation and the one exact scheme. In orange, the H adaptation and the two exact scheme, and in blue, and in green, sorry, the HP adaptation. And we can see that in most of the domain in most of the plot, we have a good agreement between HP adaptation and H adaptation with the two exact scheme. However, on the end of the domain, we can see that HP adaptation gives us a mixed result between the one exact and the two exact scheme. So as our final test case, I'm going to talk about the 2D viscous shock tube that was first studied by Daru and collaborators. So in this case, we have a square domain of 1 meter by 1 meter with a normal shock at the middle of the domain that separates a high pressure region from a low pressure region. So in this case, the normal shock is advected to the right of the domain. It is then reflected at this right wall and interacts with the boundary layer that it created in its wake, creating this very complex vortical structure. So just like the previous test case, we tested this case on a coarse mesh of 500 times 500 elements with the one exact scheme. And we compared ourselves to the results from Daru and collaborators, which obtained this result on a 3000 times 1500 elements with a 7th order scheme. So in this case, we can see that most of the details of the phenomenon are missing. So the shock is smeared. The oblique shock is, sorry, the lambda shock pattern is smeared. The vortical structure beneath the lambda shock pattern lacks a lot of resolution. This main vortical structure here lacks a lot of information. For example, here we don't have the interaction with the vortical structure, and most of the shocklets are not attached to the main vortical structure. And then finally, the vortical interaction with the reflected shock also misses most of the information. So then on top of this coarse mesh, we added our HP adaptation algorithm. So here on the left, we have the order distribution, and on the right, we have the adapted mesh with one level of refinement in this case. And we can see that by choosing a critical threshold of 0.1%, we managed to mark the lambda shock pattern, most of the vortical structure beneath the lambda shock pattern, and the reflected shock and the vortical interaction with the reflected shock at the far right of the domain, both for the two exact scheme and for adaptation. Now, if we look at the results we obtain with HP adaptation, and again compare ourselves to the results obtained with the coarse mesh and the results from Daru and collaborators, we can see some small enhancement in certain areas of the flow. So for example, the lambda shock is now much more sharper. However, we are still lacking some resolution on the vortical structure beneath the lambda shock pattern. The main vortical structure, we have a clear improvement on the main vortical structure here, which is now corrected at the correct position, but it still misses an interaction here with the second vortical structure that it needs to be attached to it. And then we have a great improvement on the vortical interaction here with the reflected shock at the far right of the domain. We also have some enhancement on the contact discontinuity here above this vortical structure. So now to further assess the performances of HP adaptation, we plot the density profile at y equals 0 here, and plot the results obtained with the one exact scheme on the coarse mesh, on the coarse base mesh, the two exact scheme with the coarse base mesh, and the results from Daru and collaborators. And on top of these three density profile, we plot the density profile obtained with HP adaptation. So you can see that there is clear improvement with HP adaptation, because most peaks, position, and amplitude are now computed correctly. However, we still have we are still lacking some resolution between x equals 0.55 and 0.65 here. But this could be enhanced by further increasing the number of the levels of refinement. So now I'm going to give some conclusions and some perspectives for future studies. So first, we have developed a p-adaptation algorithm for the finite volume successive correction k-exact scheme, which is very scarcely studied in the literature, especially for finite volume schemes. And here, in this case, it was feasible due to the iterative nature of the numerical scheme. We have also developed an error estimator that stems directly from the scheme itself, that is supposed to show us where, so this error estimator was developed to show us where we need to increase the order of accuracy of the numerical scheme. Then we also compared ourselves to another p-adaptation methods that included the zero exact scheme. And we saw that it gave us suboptimal results and can also lead us to a drastic drop in accuracy. And then finally, we successfully applied the p-adaptation algorithm that we have implemented on 2D, 3D, inviscid, and viscous cases. And then finally, we combine our p-adaptation algorithm with HP adaptation, and its application was successful only in this case on 2D viscous cases. So now here I listed three of the perspectives of this study. So the first one would be to enhance our HP adaptation algorithm. So one way to do that would be to construct a more complementary algorithm to let the solver choose whether to adapt in P or in H. And one way to do that would be to divide our error estimator to account for the errors that it made in P and one error that it made according to the mesh cell size. Next, we could also add a mean criterion and also a dynamic mesh adaptation process. So this was already done by my colleague Ariadne Liapi, but only for mesh adaptation. So one way to enhance our HP adaptation algorithm would be to implement these two for HP adaptation. Next, we could also explore P adaptation for triangular meshes, because we know that triangular meshes tend to be more dissipative than quadrangle meshes. So in this case, P adaptation would help the solver to reduce the dissipation in certain areas of the computational domain. Next, we could also explore HP adaptation with triangular elements, but that would mean also to extend our AMR to triangular elements. And then finally, we could also explore anisotropic metric-based mesh adaptation with our error estimator. So we have already done a small study on that. So we compared the meshes we obtained with the Mac-Hessian-based criterion and the meshes obtained with the reconstruction error criterion with a fixed complexity of 20,000 elements. So here, if we compare both of the meshes, we can see that the Mac-Hessian-based criterion mainly focused on the leaning edge, the trailing edge, and the strong shock, and also the weak shock on the lower surface. And our reconstruction error estimator focused in the same zones, but much more sharply, and it also focused on the upper surface of the airfoil. So this is only a work in progress, and we still need to look into it for in order to use metric-based mesh adaptation with our error estimator. So with all of that, I would like to thank you for your attention, and I'll be now taking questions.
Thank you for the presentation. Now it's time for comments and questions. And we'll start with Professor Carl-Olivier Gouche from University of British Columbia. So you can ask